How does a car drive itself? An analogy that we like to make when you ask is think about how a human works. If you think about your eyes, your ears, and your nose as the sensors, the same thing happens with vision and radar and laser on the vehicle. You think about your nervous system and how all the wires and things connect all the systems in your car together. That's like the E-architecture that we have on the car, and how do we connect the sensors with the controllers and so on. The controller is kind of like your brain, and the smart logic and the software that runs on that is really the heart and soul of how the car drives itself. Everybody's worked really, really hard to get here. This is an amazing opportunity for us. The amount of work and effort that went into this is going to be in the history books, I'm certain.
Okay, that car is the car that drove from basically San Fran to New York, all on its own, bar for 40 miles. And that is a very sweet little car. Okay, far more complicated than my little friend Johnny. So Johnny is my mobile robot, but he works in pretty much exactly the same way as that Delphi car. So anything that is autonomous and has to navigate its own environment needs to know things. It needs to know what that environment is, and it needs to know where it is in it. Okay? So that environment can be pre-mapped. So for a lot of that driving in cities, the Delphi car actually had a map, equivalent to like the Google car maps. Okay, when they were driving on highways, they couldn't map the highways. They actually had to create a map as they went along, and they had to localize in it. And that simultaneous action of working out where you are and creating a map of your environment is called SLAM, so simultaneous localization and mapping. And what we care about is where we are, so XY position, but we also need to know our orientation, which is the phi, okay, which is theta down there. So, we can do SLAM in a number of ways. We've got feature-based SLAM, so we're looking for things in our environment, so we tend to use things like sonar, radar, LiDAR. We can also use vision, so we use video cameras. We've got to worry about projection on that, because cameras curve the world. So we actually have to translate that back. Appearance-based, we can look at our orientation in it, which is pose. And we've got various different variants. The mapping bit, you'll come across Google Maps. We all know the Google cars that drive around, produce the maps for us. So we can create vision maps. Occupancy grids, really, really simple. Is there something there or isn't there? Okay, so when that car was driving down the highway and you saw vehicles on the side, that, for all intents and purposes, was an occupancy grid. It was bouncing off sonar and radar, and it was going, yeah, there's something there, and it kind of looks a bit like this. Okay, so mapping, we can do on the fly, or we can do it beforehand. Okay, so occupancy grids. We use a thing called random field presentation. Everything is probabilistic. Okay, so we're taking whole load of sensor data and going, what's the chance there is actually something there? And then we map things on. Okay. And we always include the degree of uncertainty. That's really important. The other part of this is localization. There are three key ways to do this. There's histogram filters. We can't do those when we're moving so much. Okay, we tend to do them as a one-off of where we are. The main things that we tend to do are things called Kalman's and particle filters. So we have a belief about where we are, where we think we are in the world. We take a sensor reading, we guess where we are, we work it out, and then we take into the fact that we've moved. Okay, so I'm here, I think there's a sofa there, okay, or I think there's something here. If I move my chair, go, okay, there is something there. So I can pretty much say I'm where I think I am. Okay, there is a whole load of nasty Bayesian estimators to do this. They're not here tonight, but in the fuller set of slides that are on SlideShare, all the lovely fun maths is there. Okay, so what I'm going to show you another tiny little bit of video, which is actually SLAM working. So this is Open Rat SLAM. It comes from Queensland University Technology. It's actually based on the rat brain. Sorry. that one? Right, okay, run that. Yes. Okay, so this is the map. It's taking the video data and it's actually building a map as it goes along. Okay, and as it builds it builds a far more complicated map. That one. So, I don't like using video on slides, but it helps. Okay, so let's have a quick time to run through this. With these, we have three things to do with autonomous vehicles. We have perception, decision, and control. As with everything, it is a best guess. So we get noisy data, we get incomplete data, things are dynamic and moving all the time, and we're trying to take a discrete measurement. Okay, so we're trying to kind of guess where we are all the time, but we're still moving. So our distance from objects is moving. So when we're trying to work out where we are based on our distance from objects, it's shifting all the time. So that kind of gives us some fun. So there are ways that we can kind of tell that we're roughly doing the right thing. So we come across these things called hybrid agent architectures. So we have our low-level stuff, which is basically switch the motors on and off, turn the indicator on. You know, am I still putting petrol into my engine? Am I about to slam into a wall? That kind of thing. And then we've got this thing called a rational agent, which is the high-level stuff. This is where the trust bit and the interesting decisions come in. So we can, to some extent, actually mathematically prove that we're doing what we think we're doing, okay? Which is this decision-making discrete logic bit. And we've got our external interactions, which is all the probabilistic stuff, that's all our sensor stuff. We've got our feedback and our control. But is our robot or our car doing the right thing? Mathematically, yes, brilliant. But what is the right thing? Okay, and that actually gets a bit messy. So we can say, actually, we want to prioritise things. We want humans, then animals, then we want to care about objects. What about a pushchair? A pram? What is it? Is it an object or is it human? Depends on what's in it. Yeah? At the end of the day, if it's just your groceries, we really don't care. We'd rather hit the groceries than the granny pushing the pram with the groceries. If there's a child in it, different story. What humans do we prioritise? Do we prioritise the person in the car or the two people that we might hit if we don't stop the car? It all becomes really, really messy. If we stop the car, our 6 cars are going to stack into the back of our car and hurt more people than letting us drive off a cliff and just killing us. It's a really important point. We actually have to make these decisions because if we have a fully autonomous vehicle, it's going to need to know or have a rough idea of what that is. As a human, you make a judgment call. If it's a machine, that has to make a call, but we have to agree what that call should be. Because at the moment, the legal aspect of this is very, very grey and very, very vague. At the moment, the engineer is actually responsible for the vehicle's decision. But we need to make sure we're happy with that decision. So in terms of our autonomous vehicles and semi-autonomous vehicles, they're interesting. If someone's been asleep, it takes them 20 minutes to be alert enough to drive. Should the car give control back the minute the human wants it, or should it actually make it wait? What's right or wrong? Okay, so we've got sensors and perception. They're really key things. Computing platforms and control. That Delphi car had the equivalent to 8 PCs worth of computing power running on it. Nice high-performance game PCs, equivalent of. We need to make sure our electrical architecture and network management is there. Okay, that's really important. We need to make sure the security of our network management is there. The cars need to talk to each other. That's really important. They need to know what they're going to do, how they're going to interact. A big problem is going to be if we end up with a mixture of autonomous and human-driven cars. Humans are very, very unpredictable. We don't know what they're going to do. If we've got cars talking to each other, we can keep a distance apart. We know we're going to speed up. We know we're going to slow down. We know it's going to turn left. All those kind of good wonderful things. The user experience. We didn't like things doing stuff for us. Okay, it was proved with the mouse. If we nudge our mouse and it moves too far, we don't like it. But if it moves just the right amount, It's helped just that a little bit, we like it. It was the same when they first put in the DLR. We didn't like the fact that there was no driver. Okay, so they put a human guard on there. He does nothing, he doesn't drive the train, but he's there. Okay, we're weird. How we actually do the support and services around it all really needs to be thought out. How we secure that. Functional safety and cybersecurity. You can spoof anything. You can hack anything, pretty much. We just need to make sure that we put enough controls in there to do it. Okay, so all I'm going to say is, okay, humans, we are bad drivers. Okay, 93% human error. Okay, we can get around that, but every decision these smart vehicles are going to make, even the tech you've got in your car now, is done under uncertainty. Okay, so everything is a guess. Best guess probability. Okay, we can work out where we are, we can map, but we need to work out our interactions. So between us and our car, or between the car and other cars, and between semi-autonomous vehicles. And basically that's it. Okay, and our lovely little drones that kind of get in the way and what Amazon wants to deliver stuff with us also work exactly the same way. Okay, pretty much as does an aeroplane. Your nice little Boeing 747 mostly flies all by itself most of the time without carrying the world for us. Okay, so that's kind of it, what I've got for you. There is a whole load of references. Okay, it gets a bit messy. There is a longer version of this with the lovely Bayesian maths stuff in it on SlideShare, if you want to. And yeah, if you've got any questions, really. That was a bit of a whistle-stop tour, I'm afraid.